Hi, today in this video we're going to begin a discussion about chemical equilibrium. We'll go through what chemical equilibrium is and then specifically what are Kc and Kp, which are the equilibrium constants that you'll see in any equilibrium equation question that you do. So first of all, defining chemical equilibrium. So chemical equilibrium is dynamic, right? It's not static, it's dynamic and occurs when the rate of the forward reaction is equal to the rate of the reverse reaction. So, when equilibrium is reached, the concentration of the reactants and the concentration of the products remain constant. This doesn't mean that there aren't products switching into reactants and reactants switching into products. There are. That's what makes it dynamic. But a reactant switches to a product at the same rate that a product switches to a reactant. So that's why it's at equilibrium. Note here, it does not mean that the concentration of reactants is equal to the concentration of the products. Just because something is at equilibrium and the rates are the same, that does not mean that their concentrations are the same. And we'll see that in an example in a little bit. First example here. We've got the reaction N2 plus O2, and I'll label this as both being in the gas phase, is in equilibrium with 2NO. Now, based on rate law, we can say that the rate of the forward reaction is equal to Kf, I'll call Kf for K of the forward reaction, times the concentration of N2 times the concentration of O2. And we can say this because this is an elementary reaction. And remember from rate law, if something's elementary, you can use the stoichiometric coefficients as the rate order for the reactants. So similarly, the rate of the reverse reaction is going to equal Kr times the concentration of NO squared, because again, this is an elementary reaction. So this is all rate law so far. At equilibrium, since the two rates equal each other, that means we can say Kr times the concentration of NO squared is equal to Kf times the concentration of N2 times the concentration of O2, since the rates are equal to each other. Now I'm going to rearrange this equation. I'm going to divide both sides by Kr first, and that will give me Kf over Kr times N2 times O2 is equal to NO squared. Now I'll divide by the concentration of N2 and the concentration of O2. And this will give me Kf over Kr is equal to the concentration of NO squared over the concentration of N2 times the concentration of O2. We can take this Kf over Kr and make it into a new constant Kc, and this is the equilibrium constant. The C stands for concentration, right? Because we have concentrations of NO, N2, and O2, so it's the equilibrium constant, Kc. Now I'm going to do a graph here on the next slide. The first graph will be concentration and time. And graph 2 will be time and rate. In the concentration and time graph, we've got concentration of NO here. Right, initially it starts at 0. We don't have any NO because it's the product of the forward reaction. This is the concentration of N2. And then we have our concentration of O2. At this point, when all of them continue to remain constant, that dashed line is the point of equilibrium. So notice, they're not at the same concentrations when they're at equilibrium. But we're going to go to the rate plot now. The first rate I'm going to plot is going to be Kf times the concentration of NO squared. Right, the rate of the reverse reaction, sorry. So this would be Kr, because it's the reverse reaction. This is Kf times N2 times O2, right? The rate of the forward reaction. And again, this point right here is equilibrium. The rates are the same, but the concentrations are not, right? Is it possible that you could have the same concentrations at equilibrium? Sure, of course it is. But it's very unlikely that your concentrations would happen to be exactly the same. But your rates have to be. That's what the definition of equilibrium is. So from this example, and then from the graphs we just showed, you can give a general expression for Kc. So if I say I have the reaction AA plus BB is in equilibrium with CC plus DD. We did the same generic chemical equation for rate. I'm going to say then that Kc is equal to C raised to the C power, D raised to the D power, over A to the A times B to the B. If I were to want to know what the Kc of the reverse reaction was, so right, this is the Kc for the forward reaction, right? If I were to say, okay, what's the Kc if I go with the reverse reaction? The Kc of the reverse is equal to 1 over Kc of the forward reaction. So all you do is take the reciprocal of Kc of the forward reaction to get Kc of the reverse reaction. So here, unlike rate, the expression for equilibrium depends only on the stoichiometry, right? What coefficients we have. It does not depend at all on the mechanism of the reaction. All right, so I'm going to go through another example here. Here we've got 2C2H4 gas plus 2H2O gas is in equilibrium with 2C2H6 gas plus O2 gas. My Kc here would be Kc is equal to the concentration of C2H6 squared times the concentration of O2 over the concentration of C2H4 squared times the concentration of H2O squared. Now notice, and this is important for any time you're doing equilibrium, you always need to put what state the compound is in. If all of your reactants and products are in the gas state, you can instead relate them via their partial pressures. And that would be called Kp in terms of pressure, whereas Kc is concentration. So Kp would be the partial pressure of C2H6 squared times the partial pressure of O2 over the partial pressure of C2H4 squared times the partial pressure of H2O squared. Same exact format, but now it's partial pressures instead of concentration. And there is an equation that you can relate Kp to Kc. I'll put that in purple here. So that equation, Kp is equal to Kc times RT to the delta N. Now what delta N is delta N is equal to the moles of product minus the moles of reactant. And here the moles are nothing more than the stoichiometric coefficient that you find in front. So that would be 1, 2, 2, 2. So in this case, delta N would be 3 minus 4 to give negative 1. Right? There's 3 moles of product and 4 moles of reactant. If the moles of product are the same as the moles of reactant, so if we have delta N is equal to 0, then Kc is equal to Kp, because you would raise RT to the 0th power, which is just 1. So then you would get Kp is equal to Kc. Now I want to go through one more example here that will now throw in another type of equilibrium, and that is heterogeneous equilibrium. This means that not all of the compounds in the chemical reaction are in the same state. So in this example, I've got 4 HCl in aqueous state plus O2 in the gas state is in equilibrium with 2 H2O in the liquid state plus 2 Cl2 gas. When I write the Kc for this, I'm going to get Cl2 squared over HCl to the 4th times O2. Notice you're probably saying, I forgot the water. Anything that's a liquid or a solid in an equilibrium reaction does not get included in the expression for Kc or Kp. So I'll write that down here. Solid or liquid not included in expression for Kc or Kp. The reason is that if something's in its liquid or solid form, it's in its pure form. So if you were to increase the mass of it, say I'm going to increase the mass of the water, because the water's in its pure form, the volume is going to increase by the same amount as the mass does, meaning the concentration doesn't change. So we just consider a liquid or a solid as 1 in the equilibrium expression, and since it's just 1, we ignore it and don't include it in the equilibrium expression. Now, last and very important point I want to make is oftentimes if you're taking a test or a quiz on equilibrium, you may be given a question asking if the reaction favors the reactants or the products. And the way you're able to know is if Kc is much greater than 1, that means the concentration of the products is greater than the concentration of the reactants. The expression is Kc is equal to the concentration of your products raised to some power, I'll just say m, over the concentration of your reactants raised to some power n. If your numerator is very large, meaning you get a value much greater than 1, that means you have a higher concentration of products and reactants, so the reaction favors the products. If Kc, however, is much less than 1, then the concentration of reactants is greater than the concentration of the products, because your denominator would then be much larger if the Kc is a lot less than 1. Alright, so that is it for this video. I hope you found it helpful, and there will be a few more videos that will be posted on other topics within chemical equilibrium. See you next time.